Well, good morning, everyone, and welcome to our next Blue Waters webinar on scientific workflows. This is Maxim Belkin from the National Center for Supercomputing Applications, and today it is my pleasure to welcome Ilya Solov'yov. Ilya is an associate professor in the Department of Physics, Chemistry, and Pharmacy in the University of Southern Denmark. So he's connecting to us from overseas. And Ilya is a good friend of mine. He did a postdoc here at the University of Illinois. So it is my honor to welcome him today. He will talk about the software tool that his group develops. It's called Viking. And the title of today's webinar is Viking Scandinavian Online Kit for Nanoscale Modeling. And with that, Ilya, take it away.
Yes. All right. Thank you very much, Maxim. And good morning, everyone. And that's really a great pleasure of mine to be here today and be able to report on some of our recent scientific developments that I'm pretty sure are somewhat connected to the purpose of this webinar series. So as Maxim announced, I'm an associate professor at the University of Southern Denmark from the Department of Physics, Chemistry, and Pharmacy. And I thought that it may be a good idea to start by actually saying a few words about the place where I'm kind of streaming from right now. So, I thought it would be a good idea actually to show you where is Denmark. And as some of you hopefully know, that Denmark is one of the Scandinavian countries in the northern part of Europe. So, and the city where I'm working, Odense, is especially famous for this gentleman here, Hans Christian Andersen, who is an extremely important figure in for children. So he is author of many famous children books that many parents read and present to the children. So I think that that's actually what makes Odense so special. So the atmosphere here is also really special. That all is basically connected to some sort of fairy tales. Well, I do hope that what I will present to you, I will convince you that it's not entirely fairy tale, and there is some useful component for scientific computing. The outline of my talk is as follows. So I am personally a biophysicist, a computational biophysicist, and I will be presenting Viking, that I believe is a very useful tool to do computational biophysics research. So I would start by introducing you to some general aspects of computational approaches in biophysics. And then I would like to continue by talking about workflows in computational biophysics specifically, which will lead me to introducing Viking, and basically I will explain what Viking can do, and so why it was why the development of Viking started in the first place. Then I would like to have some short hands-on session where so for those of you who had the chance to register in advance on the Viking website, there will be a possibility to explore Viking on their own. Well, I will of course provide some guidance here, and you will be able to run some short simulations of small protein using Viking environment. Later, I will then continue talking more about workflows in Viking, and if time will permit, give you some other examples of what Viking can do. Having said that, I believe I need to maybe to emphasize a little bit about what my personal background is and what is basically the area of my research, and how this area is basically motivating me to create a tool like Viking. So as a computational bioscientist, a computational biophysicist especially, I'm really interested in looking at various problems that occur in biophysics. And having said that, so I would like to draw your attention to this diagram at the bottom of the slide, where you can see basically a workflow, if you like, that takes us from one scale to another in biophysics. So basically, on the very right part of the slide, you see the scale of molecules, and those colorful clouds here are supposed to represent electrons. So this is what is basically one of the smallest scales that you can imagine in biophysics. Then we can scale up and go all the way up to the scale of organisms. And in my group, we do use computations to bridge scales between these different objects. So I'm not really going to talk a lot about the scientific results that we obtained. I would more like to focus more on introducing the computational developments that we did, since the aim of my webinar here is to talk about the computational suite Viking, which is basically the suite that allows us to do these complex multiscale simulations that bridge the scales from molecules to the higher ones. So I would like to emphasize that in biophysics, all the processes that you can imagine are actually governed by the fundamental laws of physics. And biophysics is not an exception, so you can actually imagine a lot of different processes that can occur on nanoscale, and here I summarize some of them, that all should ultimately fulfill the laws of physics. And basically, if you're interested in a specific process, so you could define a certain observable that can be described by appropriate equations. The big challenge here is that you often require powerful computers to solve these equations, and so Blue Waters, of course, is a great tool to be able to do so. And then you also need to have a really powerful software that permits you to solve the equations. And well, in this slide, I would like to emphasize MBN Explorer, that software actually allows you to do a lot of different simulations on different scales. And so biophysics would be just one example here. But of course, it is not the only software that you can use for doing complex simulations. And in my webinar today, actually, I will be talking about some other programs as well. So talking about fundamental laws of nature, fundamental laws of physics. So well, here I would like to show you this very general slide, where basically I would like to emphasize what fundamental laws of nature one can think about when you consider different processes. And again, so biophysics is not an exception here. So classical mechanics follows the Newton law of motion, while quantum mechanics is governed by the Schrödinger equation. And depending on the problems that you would like to solve, you need to choose the appropriate equation, and then we'll have some possibility to solve that. So basically, this in the very general, in the very crude terms, would be then the approach that you would like to do in order to solve complex problems. If we talk about the Newton law of motion and the Schrödinger equation, I would like to give you two examples here, where I would like to emphasize how the Newton equation and the Schrödinger equation actually apply to biomolecules. So I hope you can see these two videos here. And so in this right video, you see this colorful cloud, colored blue and red, that jumps from one molecule to another. So this is a result of a real simulation. So where we used quite advanced computational techniques to solve the Schrödinger equation in real time, and to be able to describe how an electron can propagate through a specific biological molecule. The other example is actually inherited from Wikipedia, and it's supposed to illustrate the atomic motion. So in this case, since atoms are much heavier than electrons, you can employ the Newton law of motion and describe the motion of atoms essentially using classical equations. Here, it's very important to mention that this type of observables would be very difficult to obtain by using real life microscopy. So just imagine what kind of microscope should enable you to visualize the motion of electron in a real biological system. So it's very challenging process, and computations are luckily are able to provide us with this kind of output. Also, the atomic motion on the scale, when, for instance, we are considering motion of individual hydrogens in complex biological systems, is very difficult to resolve experimentally. So, in a way, you can consider that computations in biophysics provide us with a tool that some people quote as a computational microscope. And this computational microscope has become increasingly prominent in the last years. And I would like to refer to this nice illustration that I have inherited from Klaus Schulten when I still was working in Urbana, that basically illustrates how computations have evolved during the last decades, and what kind of molecular systems they are able to solve computationally nowadays. Basically, there are a lot of motivations why should we study computationally biological and biophysical systems. So here I just summarize some of them. well, I mean, this list can continue much longer. And I would especially like to emphasize that using computations, we do have the full control of our systems, and so we are able to supplement experimental discoveries by providing new insights that otherwise would be impossible to obtain. So I introduced you to this term computational microscope, and here I actually would like maybe to elaborate a little bit on that. And basically with this slide, I also would like to mention a little bit, so what kind of workflow you can envision when you employ this computational microscope. Well, first of all, as I mentioned, that okay, if you study biophysics, biophysical systems, so there are fundamental laws of nature. So basically, we have physics in the problem, and basically physics gives us the equations of motion that have to be solved. Then this physics has to be coupled with some chemistry that basically will define us how do the individual atoms interact in the case of biophysical biological systems. Then once this is done, it's very important to use the right mathematics to be able to solve the equations of motion. And I mean, here you can envision many different ways how you can solve numerically, for instance, this law of motion. And I mean, some ways are definitely better than the others. And it's very important here that the mathematics is done efficient here, because if you are considering looking at the dynamics of molecules, you need to solve this equation many times. Like for instance, if you solve the Newton's equation for a complex biological system 1 billion times, well, then you will obtain a molecular dynamics trajectory that would be worth maybe about a microsecond. So it's very important that the underlying algorithms for solving these complex equations are very efficient. And then the last two parts are also critical. So you need to have the software that allows you to solve these equations. And for example, the software NumD, developed at the University of Illinois, is a very popular software that many people all over the globe use. And so here you also can see well, how this software can perform if you start using that on supercomputers. So supercomputers is the last component of this computational microscope workflow that enables you basically to do these exciting simulations. And as you probably noticed on the previous slide, I noted some systems that are of the size of millions and even tens and hundreds of millions of atoms. So these biological systems are possible to put inside of a computer nowadays and do all atom simulations. And I mean, the reason for that is that so now we really do have extremely powerful computers that didn't exist 10 years ago. So I just mentioned that so in the case of classical molecular dynamics, so well the sizes that we can handle are really huge. So one of the largest simulation was actually done by the group of Klaus Schulten, also from University of Illinois, and it included about 100 million atoms. The case is more is actually quite different if you now start looking at things quantum mechanically. So quantum mechanics is basically another niche, if you like. So it takes you to a different scale in the case of biological systems. And in this case, so we actually do lack some of these components that I mentioned on the previous slide. For example, all the existing software for quantum chemistry, they would not permit you to scale so nicely to large systems, and this basically limits the sizes of the systems that you can study. And also, if you try to do quantum chemistry on the most powerful computer, that actually often doesn't really bring much, because the codes are just not suitable to run on these huge machines. But very important is that these two scales, the classical scale and the quantum scale, they often need to be interconnected. They need to be linked to each other, because so there is a lot of information that goes from one scale into the other that determines how things behave on even larger scales. So also, I think it's really worth mentioning in my introduction here, so that actually the number of papers devoted to computations has really risen a lot during the last years. So basically, on this graph here, so you see the number of papers published every year that in some way quotes the word molecular dynamics. And well, I think I would be correct by saying that this is sort of an exponential growth. And so, well, just 2 years ago, well, there were like 35,000 manuscripts published that somehow were dealing with molecular dynamics. it doesn't only involve biological systems. Molecular dynamics is quite a broad term that can also be used to study things on nanoscale. And so I'm pretty sure that this plot can be split into different subsections, but the trend probably would be more or less the same for all of them. Also very important to mention that different software that are used for studying biophysical problems computationally has gained increasing interest in the last years. So here you can see some popular software. Actually this list can be easily expanded by many other names. All right. So if simulations are so important, and I mean if you really can learn so much from the simulations, I mean there is a natural question. So why do not everybody use simulations in their daily scientific work? Well, there are a few reasons for that. And here again I summarize maybe some of the most prominent ones. So for instance, if you intend to study things computationally, you need first of all to be aware of what software would be suitable to address your problem of interest. Then you need to be able to solve a lot of technical questions. Like for example, you need to be able to provide input files for the programs in the right format using some very specific keys. In some cases, these keys would be absolutely meaningless. So you really need to know and understand the program, which often involves quite extended time of training and educating yourself. You need to have access to supercomputers, of course, if you intend to study large enough systems. So, I mean, of course, you can also do some computations using workstations, but so if you intend to do multi-million simulations, this is hardly possible. And you also need to understand what you actually can learn from the simulation data once you obtain that, because often the data that the programs provide as an output are quite big in size, and you really need to know what to do, because I mean, again, there are a lot of technical issues that have to be solved here. So in a summary, so I probably would say that the simulation protocols and workflows that you need to employ to do computations in biophysics are sometimes quite difficult to comprehend. So you do need some training for this. And here is one generic example of a workflow that kind of summarizes what probably some people could do if they intend to do some protein modeling. So if you have a question that is related to protein modeling, I mean, there are different sub-questions that you can answer. And this diagram basically leads you through different possibilities. And as you can see here, it's sort of like a tree that expands. And I mean, what I show you here is actually just a small fraction of the entire tree of possibilities that you can do if you are interested in doing a problem related to protein modeling. So, and all these boxes, actually do require some specific knowledge. And more than that, so these specific boxes that you see on the slide actually are also diagrams and workflows by themselves. So, for example, if we look at the workflow for molecular dynamics, so you can see here there is a diagram that has a lot of items in it. So I don't expect that you would be able to see the details of all of them. So I think that this is actually a workflow that you would do if you use a program Gromox. But so here, just a summary. So there are these 5 stages that basically every person has to undertake if you wish to do some molecular dynamics of, let's say, protein systems, or maybe, some systems from the area of biophysics. So all these small boxes basically mean that you need to have some action. You need to do something in order to progress through this workflow that I'll summarize here. So, and if you, for example, if you are an experimentalist that have a very clearly defined system of interest, it can be quite difficult and quite challenging for you to actually understand what do all these labels mean, because some of them actually are quite specific. Another example is shown here is a workflow for homology modeling. So it looks a bit simple, but again, so all of these boxes here can be expanded, and this is just a summary illustration of what one encounters if you intend to perform some homology modeling of proteins. So, having said that, I also would like to emphasize that it's not only about creating this input files and going through configuration of the of the specific scientific program, it's actually also very important that a person that intends to do computations, he is at least a bit of a computer scientist. So you need to be able to run some small scripts. You need to be able to work in a terminal. You need to be able to submit your jobs to a supercomputer, and you need to understand how a supercomputer works, because otherwise you could probably screw up, and then well, the administrators of the supercomputer would not be happy and ban your account eventually. So I mean, there are all these small things which add up, which actually make computations not so easy after all. So, and basically this takes me to my motivation slide, why we decided that a tool like Viking could be very, very useful for the scientific community. So Viking was intended to be a software that tries to eliminate as many as possible of those small technical problems that you can experience while you construct your simulation, you run the simulation, and then do the analysis. So the very basic workflow of Viking is actually shown here. So just imagine that you have a problem of interest, some biophysical problem. So in this case, the illustration is supposed to show that, well, for instance, you're interested to understand how olfaction or the sense of smell work. So then you possibly know a little bit more specific what you would like to investigate. Like, for example, you would like to investigate how a ligand, like an odorant, would bind in a specific olfactory receptor. Then Viking will, basically the idea of Viking was to construct a very easy setup for the user to prepare all the needed information to run simulations. So I call it plug-and-play setup, inheriting the name from older versions of Windows, when you were supposed to plug something in, and then it would miraculously supposed to work. So, but this is also the idea of Viking, that basically you provide Viking with some basic information, and then it does the rest for you. Once the simulation data is prepared, so Viking should handle calculations on a supercomputer, and for this purpose we basically wanted to establish a clear link between the Viking software and essentially any supercomputer that the user would like to define in his Viking account. As soon as the computations on the supercomputer are finalized, it's also very important for the users to be able to use the data. And for this purpose, we wanted to incorporate in Viking some algorithms that would allow the user to use visualization techniques, modern visualization techniques, to be able to assess what kind of data he or she obtained. And here you can see the illustration that somebody is using an iPhone to control a piece of a DNA molecule on the screen. So this is kind of our goal, where we would like to head, that you can use something like a tablet or like a smartphone to be able actually to understand the output of the simulation. So basically, there are a lot of limitations that we hope will be solved by Viking. For instance, the existing software are too specialized. Then, we try to take all those technical problematics into the advanced algorithms that will be implemented in the code. So also very important to mention that some software in computational biophysics especially are not just a single program. So very often you need actually to rely on different software that work together, and you need to have one software provide output for the other software to be able to solve more challenging and more exciting problems. So we try to also solve this problem with Viking by making it possible to interlink relevant programs together. Like, for example, link classical molecular dynamics with some quantum chemistry is a very important task, which allows you to bridge the scales between quantum and classical systems. All right. Well, this is a short summary also of the workflow that Viking basically contains. And very important to mention here is that Viking is a program that was designed from the very beginning to be a web-based platform. So by this, we hope to eliminate the problem that you don't need to install any software. You don't need to install any specific software on your machine, which actually also causes a problem sometimes, because some programs that you need to install are only existing for Windows, some are only existing for Linux. There are also all issues related to driver versions and so on and so forth. So by developing a web-based application, so we believe to solve this problem. So basically, that any user can get access to Viking and then use it to do some simulations, as I just described. So, and Also, Viking is actually linked to some standard databases, like for instance, Protein Data Bank is important to mention here because it provides input for many structures of proteins. So, and by having a direct link to the Protein Data Bank from the Viking, it actually makes easy for many users to start looking at some specific systems, some specific protein systems. All right, well, at this moment, actually, I would like to pause my presentation and actually go to the next part, where I would like to present you some tutorial how you can actually use Viking to do some simulations of a fairly small system, protein ubiquity. So some people actually asked for an account in Viking in advance. So, well, I do believe that we have enabled all these accounts. And these accounts were created specifically for the purpose of this presentation here. So they're not fully functional accounts in Viking, and so the reason for that was basically to make sure that people actually can follow the steps that I will be presenting right now and be able to go through the process of setting up simulation and then also hopefully visualize some simple results at the end. So the first thing is one needs to log in using the username and the password that that all the registered users obtained from us before. So, and once this is done, so you can log in and you get to the front page, the so-called dashboard in your Viking account. So the dashboard is basically a summary of your different computational projects. So, well, depending on the different computational tasks and projects that you set up in Viking, so well, this dashboard will actually expand and will contain more information. So what I would like to do now, I would like to go here into projects and create a new project. So I will try to be slow here, so and I hope that those of you who obtain the account would be able to follow me. If my pace would be too high, please let me know and please post a question, and then I will try to slow down a little bit. So the first step is to create a new project. So we do it by going into projects, new, and first we need to define the name of the project. So let me just call this project test. And also, in principle, so you have the possibility to write some description for your project. So if you intend to have many projects, it's a good idea because then you would be able to easily identify so what the project is about. So once the project is created, so we can actually see it here in the list of projects, and I can select it now by clicking on it. So this takes me to the page of the project test, and as you can see, the project right now has actually no tasks defined. I mean, this is obvious because, well, I mean, this is a new project, and what I would like to do now, I would like to define a new computational task by choosing the new option. This takes me to the next page where I can see 4 tasks that were enabled for the purpose of this webinar, and we are going to focus only on the first one, the molecular dynamics task. So you choose molecular dynamics, and once you do so, you are taken to the first step of the Viking Wizard. So the Viking Wizard is basically the core of Viking workflow that takes the user step by step through different questions that he has to answer in order to be able to construct all the relevant files that later will be used for simulations. So, well, I mean, I can just keep the default name, or I can also put here a different name if I like to. Okay, let me just put here MD1. Then I go to the next step of the wizard, and at this stage I need to define the structure of interest that I would like to investigate. So as I announced, I want to study a simple protein, ubiquitin, and I can do so by clicking the new structure button. And here I have the possibility either to upload the structure file of the protein, or I can download it directly from the protein data bank. As I mentioned before, Viking has a direct connection to the protein data bank. So this means that I can just type in the PDB code of the protein and click load. This will immediately show the protein in this molecular visualizer. So you can see that so once the protein structure is loaded, I can also then rotate and zoom into the structure. So basically, I can see if this is actually what I like to use in my simulations. At this stage, it's also possible to access a molecular editor by clicking this magnifying glass button. So if you do so, So we get a new window, and then you see this protein is basically occupying all the space in your browser window. And again, you can do some simple things like rotation, translation, and zooming in. But you can also do some modifications on the structure by clicking this icon here. So this allows me to actually start doing some modifications. For example, now I click on this atom here, and I would like to translate it. So I can do so by choosing the move to option, and then you can see that. But basically, the viewer, this editor here, it also contains some possibilities for editing your structure, and we continuously are working on expanding the possibilities. So at a later point, I do believe that we will have things like introducing mutations into proteins, and also, it will be very easy to be able to dock two structures together, so that this will enable more sophisticated computations. All right, once the structure is set and modified, we can proceed with the next step of the wizard, and then so here at this next stage, so you need basically to tell Viking what kind of system you are simulating. So in this specific case, we are working with proteins, and basically here I need to say, okay, we have proteins in our system, but we also could have water. So for example, this could be crystalline water, or it can be the additional water that you would add into your simulation. So if you intend to solvate your system. So this is often done in the case of computational biophysics, since we rarely want to simulate things in vacuum. The next step will basically allow us to define if we would like to simulate the protein in a solution. So in the case, we can choose water, or we would like to do it in vacuum. So for the purpose of this webinar, because I kind of wanted that, so the people who actually got the account have the possibility to visualize the results. So I think that we will do it really simple. So and we are going to discard this possibility of actually solvating the protein, and we will just consider the protein as such. So for the real simulations, of course, so you would like to choose water here, and then you have the possibility to define the solvation box. So basically defining how many water molecules you intend to place around your protein. So all right, so let's now proceed to the next step. And so here we need to define the overall duration of the simulation. So again, for many realistic simulations, so you probably would like to do simulations which would go beyond nanoseconds, in some cases even beyond microseconds. Because and here, there is this illustration sort of, to summarize how long you should be possibly running your simulations if you would like to observe a certain effect. For the point of this presentation, I intentionally would like to put this time very short. So actually I would put 0.1 nanosecond, which wouldn't permit us to see anything reasonable, but maybe just some few steps in the dynamics of the atoms. But again, so we would be able to run the simulation within like 5-10 minutes. So once we are done. So now we need to define the temperature, and here I will just use a standard value for the temperature as 300 Kelvin, and also pressure. So I mean, these characteristics are important because, especially if you are doing this more realistic simulations in water, so that you probably would like to see what are the conditions at which you would like to have your system to move. And I mean, for the purpose of this webinar, so we'll just use a standard 300 Kelvin value. But of course, you can use any value. All right, and basically that takes us to the very last step of the protocol. So this is the summary page. So the summary page is intended to basically to list all the inputs that you have provided, and basically it allows you to do some modifications before you do run the actual simulations. So here you can see some tabs, and these tabs are related to these different stages that you typically do when you run molecular dynamics. So I also mentioned a little bit about equilibration and minimization. So this is all summarized in these stages here. So also usually, so when you don't really want to go in these individual stages, because we use some standard values from some established protocols for running simulations. and it actually works in 90% of the cases. In the case if you would like to do something more specific, you have the possibility to go and actually to change all the parameters, also those parameters which are probably more special. And for instance, if you're a more advanced user, so you have the possibility to actually to influence the input of the program, and this can be done by clicking at the individual stages here and then modifying the relevant parameters. What I would actually like to do, I would like to modify the standard parameters a little bit, just to make sure that actually this simulation will complete in short time. First of all, I go in the first stage of minimization, and instead of having the default value of 10,000 minimization steps, I will put 1,000 here. Then also I would like to change the simulation length for the first stage to 0.01 nanosecond. This is extremely short, and well, this should never be used for any reasonable simulations, only here for the purpose of demonstration. I do the same for stage 2, where I change the simulation duration from the standard 2 nanoseconds to 0.01 nanosecond. And lastly, I do this modification for stage 3, where I again put 0.01 nanosecond. So I think that once I've done the small modifications, I go to the general options again, and here I would like to draw your attention to this specific part. So the part called resources. This is where, so I would like to run the simulations with Viking. And so this is actually where you are supposed to have a drop-down list of different supercomputers and different resources that your account may have. So for the purpose of this webinar, so we intentionally enabled the single resource that is our internal Viking server. So our Viking server is a small resource that we have here internally at our university, where we can run some small simulations. So in the more realistic scenario, so you should actually have some mentionings of some supercomputers, and once we submit the simulation, I will actually comment on that, how this list can be expanded. All right, so basically, I just click the Run Task button, and so at this point, the task is being processed, and you see, I actually see some warnings that basically tell me that it's not a good idea to use periodic boundary conditions without a solvent. I mean, so Viking also is constructed in a way that we try to warn the user if there could be possible issues with the simulation files, because sometimes the user, for example, may be not aware that so in realistic biophysical simulations, it's a good idea to add some solvent. And so this is the reason why we try to analyze the input files before actually, well, the user spends a lot of computational resource on running simulations that will be useless eventually. And then you see another notification that was created, basically stating that the execution of task MD1 has now started. So, well, we can close this notification to, well, avoid some cluttering. So now the status of the task is running, and you can also go to the events log, where you can also see what is actually happening with the task. It's being updated dynamically, and you see that actually we are already at stage 2, meaning that so the first stage is complete. And well, as I mentioned, I mean, I intentionally put these parameters very low to be able to see some output very fast. Also, if you go to your dashboard, you're able to see the status of the active task, which is MD1 in this case, and you see that it's running. All right, while it is running, and I think that the envisioned time for completion is about 9 minutes. So I would like to comment a little bit about adding computational resources into your Viking account. So here in the Viking menu, so there is this icon here that a user can click, and this allows you to go into your settings. So if you go into your settings, you actually see a tab called Resources. So Resources is a place where you are supposed to add supercomputer allocations. I mean, this can be, for example, an allocation on Blue Waters, can be an allocation on some cluster, well, here in Denmark, can be elsewhere. So, well, right now we do have some support for those clusters that we actually used in my group, but so the interface that has been created is rather general. So, in principle, if a user has an account on some specific supercomputer, it is possible to add this resource, maybe at the current stage with some help from our side, but so this is not really something that well is a major issue. So if I click this Add Resource button, I can actually see a form where I have the possibility to choose a resource from a predefined list of resources. So you see two options here that are grayed out because I'm using a test user account for the purpose of this webinar. This is Abacus 2.0 and Blue Waters. Abacus 2.0 is a supercomputer that we use here in Denmark, and Blue Waters you all surely are aware about. So if I would be using a real Viking account, I could then just select this computational resource, and then there will be again a very intuitive step-by-step procedure that would allow a user to link an existing account on the supercomputer resource to the Viking account. All right, so let's have a look how this task is doing. And so here, if I go and click on the MD1 task, so you see actually that, well, we are already in stage 4. So it means that, so probably soon, so the task will complete. So I think that, well, maybe while it is running, so we will get back to that. I will just use one of my previous completed tasks that I have pre-created also for the purpose of this webinar. So let us actually have a look at this completed task MD1 ubiquitin in water. So basically this is the same simulation, but here I did put water around ubiquitin, so it's actually a more realistic simulation. So if I select this task from the dashboard, and you can see that so the status of it is done, I can then go to the next page, and so here I see some tabs, and in particular interesting is the view results button, or sorry, view results tab. So I can select this view results tab, and this takes me to the summary page where I'm supposed to see the results of the simulation. First of all, you see this molecular viewer that shows the structure that was simulated. So you can see some blue, well, I hope you can see it on YouTube, that it's not of extremely poor resolution. So there is this blue shaped something. This is a protein ubiquitin inside of a clouded water environment. Also, you can see that these are actually all the 4 stages that were simulated, and I can select, for instance, the production stage that is of most interest, I assume. Also, here you can see that there are different tabs that allow you to look at some standard results like total energy evolution as a function of time, RMSD, and well, this list is also actually continuously expanding. Well, as soon as we implement new methods, so we are able to also provide some standard output here on this result page. Let me click this magnifying glass here, and this actually will take me to the visualizer of the production run simulation. So, well, first of all, what I would like to do, since it's not really nicely represented here, because the water molecules just make it impossible for us to see this ribbon-shaped protein. So I can click this link here, and here I can choose different representations for the parts of my system. And for example, I can choose to show solvent in lines representation, and I click update representation. So this allows for a more simple visualization for water, but then, I mean, we do see the protein much better. And also, as you can see, I can actually basically rotate the system smoothly without any delay. So here, very important to emphasize is that, well, I actually operate with the data that is currently located on the Viking server. So I have nothing stored locally. So basically, every time that, well, you see something appears on the screen, it's actually streamed from the Viking server directly to the screen. Also, since this was a result of an MD simulation, so of course we would like to see some dynamics, and actually we can do so by changing the time instances of the simulation by clicking these buttons here. So you can see that actually things behave dynamically, so that basically the protein wiggles a little bit and the water molecules move around. So this is a very important feature of Viking, that actually in this case we do stream the molecular dynamics trajectory on the web while I'm presenting it to you. So our goal is that we would like to enable this streaming functionality, that you would be able to see the molecular movie of also much more complicated structures. And I do believe that we have support well, up to maybe about 1 million of particles, depending how you would represent them. So in some representations, of course, it would be impossible to stream this large amount of data. But in some more simple representations, this is actually doable. All right, so I do hope that our task has now completed, or it's actually still running. So, so yes, well, maybe it will take a few more minutes. And All right. Well, maybe then I will just go to the basically the same task that was actually also created before. So also in vacuum. So you see, as soon as the task completes, so you always have this view results button. So and in this case, so in the case of this ubiquitin in vacuum, so you will just see the ubiquitin, and so then well, no water molecules would be shown. So basically, Viking also does analyze the different components that the system that you're studying has. And in this case, if I would like to change representations, it would just show proteins, because actually this was the only component that was simulated here. Also, it's possible to show the protein in a different representation. Like, for example, we can use balls and sticks, which will actually allow you to see the protein in all atom representation. So also here, so we actually have this possibility to use the output of this existing task as an input for follow-up calculations. So I will actually talk about that a little bit later in a moment, because I would also like to show you how you can use the output of an existing computational task to run some further analysis using Viking. All right. Well, actually, while I was presenting this to you, so I got a notification that task MD1 has completed successfully. So we can go to it, and you see that we actually have now these two new tabs appeared. The view results tab I already showed to you on some other examples. So well, it will be nothing really new. So basically the protein, and so we can, for instance, choose production part of the simulation that will then allow us to actually observe how the protein was behaving in this short simulation. So but then also I would like to actually to mention that maybe some more advanced users would really appreciate the possibility to have access to the output files that the different programs that Viking uses has produced. So you can do that by going to this view files tab, and you actually have the file structure of all the simulations that were performed. So basically, you see here stage 1, stage 2, and stage 3 and stage 4. So if you click on the folder, you actually can download all the output files. And if you consider yourself as an advanced user, so then you probably would also know what these files mean and how you can operate with them. So I think that this part summarizes my hands-on presentation. So let me now go back to my PowerPoint slides, because I still have a few other things I would like to show to you. So okay, so basically the idea of Viking is that it's sort of like an umbrella that actually embeds links between different existing software. So it doesn't actually contain any unique algorithms for running MD simulations or quantum chemistry that I will also present to you shortly in a moment. But instead, it actually relies on the existing software that have been established reliable for different areas of application, and then it provides the user a nice interface to be able to run simulations with the software, and also important to mention to connect one software with the other. So some of the software that you see here, I mean, we already have incorporated into Viking infrastructure. Some of the software is still in progress of we're still developing to be able to push it to our production server. I already mentioned to that, but also I would actually like to show this screenshots that Viking works exclusively through web browser. So I do believe that this is really an important achievement, because you really need to understand that web browser has a lot of limitations, and we try really to push it to the edge. That basically we use all the front end techniques that would permit the user to visualize quite complex molecules, and also basically to work with molecular complexes like you can see here. So this is actually a protein assembly that you can visualize in Viking. So I cannot tell you how many atoms it includes, but it actually works almost the same way as ubiquitin, so that you can visualize the trajectory of the molecular dynamics simulation if you have one. So the very key part, and I was also actually so when I was presenting Viking on some conferences, actually I received some comments that this is sort of like a black box, to some people, but I would like to comment on that specifically. So is this part in the entire workflow that I call data preparation and results aggregation. So as you've seen through the wizard, the questions that you answer, are quite simple. So you provide information about temperature. So you provide information about pressure. You maybe specify the type of solvent that you would like to use. But I mean, of course, when you run simulations, for instance, with NumD, there are also a lot of other things that you need to take into account. A lot of technical algorithm-related issues that have to be solved. And as I mentioned, I mean, we use in most cases the standard protocols to handle this situations. But I mean, of course, a user has a possibility to change all the parameters at the Viking summary page, and to make sure that it's actually not a black box, as I mentioned, we try to provide a lot of hints and supplementary information for the users. For instance, so when you go through the Viking Wizard steps, you always have the possibility to click on some question marks around that are supposed to give you some idea what is actually behind this specific question and what are you providing to the program. Also, we do have on our Viking website some video tutorials, which the idea of these video tutorials was to basically to show to the people what kind of workflows we use, but also what kind of algorithms are actually behind this data preparation and results part of Viking. And I mean, of course, since we are relying on well-established software like NumD or Gaussian, there are a lot of very specialized tutorials that will actually teach people a lot of details about these programs. So we are, of course, also referring to those where relevant. So I do believe that all this together makes this part not really as a black box, but actually quite a useful tool for some people to run simulations. All right, I did already announce about that, but actually I also would like to show you a little bit how it actually works in real life. So I still have a few minutes, and I don't think that my presentation will be very long here. So basically, if you have a project like the one that we've just discussed with you, and you've run molecular dynamics on some structure, and maybe you would like to then do some additional analysis, like maybe you would like to do some quantum chemistry, or for instance calculate vibrational properties of a certain part of your molecule, then you can totally do so through Viking. So let me again show you this by going back to my Viking account page. Unfortunately, this cannot be repeated in real life because the software Gaussian that I'm going to use now, our group has a license for that, but I wasn't aware if all the people that signed up for using the hands-on part have the license, so we had to limit the access to that. So I think that I will just present this part myself. Okay, so I will go in this completed MD task of ubiquitin in water, and then I go to the editor part where I would like to look at the production part of the simulation. So I open the editor, the molecular editor, and I would like to zoom into the system that and just for the purpose of this webinar presentation, I would like to calculate the the optimized structure and then the vibrational properties of one of the water molecules that you can see here. I mean, this calculation can be completed very fast, and I mean, of course, it probably is not very useful, but I think that it will serve the purpose of presenting how Viking can do that. So first of all, I need to select the molecule of interest. Let, for example, this molecule be this central water molecule that we can see here. And then I have this magic wand icon that once I click on that, I have the possibility to select a new task, and I will use geometry optimization first. So once I have selected that, it takes me to the Viking Wizard, and now I need to follow the new workflow of setting up geometry optimization in Viking. So this wizard is much simpler because actually it requires much less parameters. And first of all, we provide it with a structure, which in the case of my test presentation here is just this extracted molecule from the previous MD simulation. As you can see here, this is the water molecule that we have selected. Then we proceed to the next step. So we need to tell that the molecule is electrically neutral, so the charge is 0. And we need to define the multiplicity. And again, you can actually go here and read more what multiplicity is if you are not sure about that. So then we provide some information about some quantum chemistry methods. And so I would just select this method ChemDisRelib. And also we need to provide the basis set. So all these things may seem to be quite technical, but we also try to actually improve this page a little bit in order to provide people with more insights about what stands behind these labels, so that they would actually be able to progress through this Viking Wizard more easily. Okay, so now we are done. And so here, again, I can use Viking server for running my simulation. So I submit it to the Viking server. And so once the files are processed, we see a notification that the execution of the geometry task simulation 1 has started. So if you go to the events log, so you see the simulation basically completed instantaneously because it was actually fairly small. So now we can go to the view results part, and so you actually can see this molecule again, and we do have the possibility to visualize how the structure of the molecule was changing while I was performing the structure optimization task. So you see some atoms moved a little bit. So, but now if I would like to use the this structure for frequency calculations, so I go here to my project, and you see that geometry optimization simulation 1 is among my completed tasks. I click set new task, and I choose frequency calculation as my next task. So here at the frequency calculation, I select the optimized molecule that was obtained in the case of the geometry optimization before, and then I proceed with the Viking Wizard. Again, I need to answer the questions, and it's important, of course, that I use the same method for frequency calculation as I used for the geometry optimization case. All right, so now I do run this task also, and as I announced before, that it's probably going to complete rather soon. Yes, so it's done. So let's have a look at the results now. So I go again to this results part. I open the editor, and now you see some additional information. So you see these yellow arrows that actually are supposed to illustrate the normal vibration modes of the water molecule. So since water molecule has 3 vibration modes, you have the possibility to actually browse through them, and so you actually instantaneously see how these different vibration modes would change. So how are the atoms supposed to move? So in this case, it's very simple. So it's in the case of water molecule is extremely a simplified one. But of course, you can also do it for more complicated cases when, for example, you would select a part of your protein and then do some similar analysis. All right, so I think that I am closely getting to the last part of my presentation. So I think that I don't really need to talk much more about this part because I already mentioned several times that Viking does use computational resources, external computational resources like supercomputers, and so basically this is also very important component that you can actually have this very easy link between your Viking account and some supercomputer accounts that enables to run simulations. All right, so this is my almost last slide where I would like to summarize what I presented to you today. So that Viking is actually a tool that relies on some workflows. So some of these workflows actually are rather sophisticated, and they are very include very interconnected steps. So basically, depending how you answer one questions on one step of the workflow, you will actually progress differently through this complicated tree of setting up multiscale simulations. So, and that means there are, of course, some nice features of Viking, like for instance, you are able to visualize results through the browser, and you don't really need to configure any specific scripts to do some basic analysis. All right, I think that my time is out now, so I would like to thank very much my group with whom we were working now for about 2 years on making Viking possible and basically getting to the stage as it is right now. So I especially would like to thank Vasily, Peter, and Emil, who were actually behind many of those algorithms that I presented to you. But in fact, so Viking is actually a project that involves all the people that you see on these photographs, and also some other people that were there at the initial phase of this project. So I do thank all of them, and I also thank you very much for your attention.
All right, thank you, Ilya, very much. It was a very interesting webinar. We had a small discussion here on Slack, and I would like to ask a question that actually sort of started there. So, what if a person wishes to do some simulations using software package that requires a license? How does Viking handle that?
So this is actually a very good and very important question, because right now our policy is the following: that so the Viking account as it stands right now, so it is free. So basically, a person can get an account on Viking, but then so it is the responsibility of the user to have an access to some supercomputer. So we are not able to provide an access to the supercomputer allocations that, for instance, my group has. So basically, a user has to have some connection to a supercomputer. If a user has that, so then he or she can set up a connection between the Viking account and the supercomputer, and then so if a user has a supercomputer account, well, basically this user probably also has some possibility to access certain software. Or, I mean, if the user has a license for specific software that is not installed on a supercomputer, then this user can get in contact with administrators of the supercomputer and make sure that the software is installed. I mean, of course, this is also, since Viking is actually in dynamic development. I mean, if the user has a license for the software, and there are some issues on a specific supercomputer to install it, I mean, our team can also help here. But it's the responsibility of the user to obtain the license, and then basically to make sure that this software is actually existing on the supercomputer. So for the different tasks that we support in Viking, we also provide some documentation what kind of software is actually needed for running the specific tasks. So if, for example, a user creates an account on Viking, and maybe he has access to a supercomputer, and then he tries to run a task, and then so his account on a supercomputer is missing a certain software, then the user will actually get a notification that there is a problem, and the user will be aware that he has actually to add some specific software to his supercomputer account.
And I have one more question. So a lot of, let's say, majority of supercomputers, they use modules to install software. And frequently, a user has to use different tools for different tasks that require different modules. For example, to run a certain tool, I might need a certain compiler or something like that. So how would Viking handle such a situation when a user needs to load different modules, things like that?
Yeah. So this is also a very good question. So basically, this is why. Well, actually, this takes me back to what I mentioned, that so in the case if a user has an access to a supercomputer that is not currently in the list of those that we're already supporting, then it's a good idea that the user actually gets in contact with our developer team, and we actually solve some technical issues initially. The reason for that is because so when you actually set up this template to access a supercomputer, so we check carefully how you can actually make sure that a certain software can run on this supercomputer. So what modules would the user be needing to enable to add to, for instance, to be able to run NumD or maybe to run Gaussian. So and in the case of, for instance, Abacus, this is our Danish supercomputer here. So we basically we made sure that for all the tasks that that we have, so this pre-settings are configured in such a way that all the needed modules are loaded. So if somebody would approach us saying, okay, I do have an account on Titan, for instance, so I mean there would be no problem to add Titan to the list of this supercomputers, but I mean it may involve some actions from our side to make sure that the right modules actually are loaded for users that actually intend to use Titan for the computations.
All right. Thank you very much, Ilya. It was a really interesting talk, and it was a pleasure to listen to it. Yes, so, again, please join me in thanking Ilya for his wonderful webinar today. It was very interesting, and I look forward to people using your tool. I'd like to remind you that there will be no webinars in July, so you can take a month off and enjoy summer. Please check Blue Water's webinar site for the announcements about webinars that are coming. We have a few that are already scheduled for September. And I will send you a link to a short 5-question survey after this webinar. You, in fact, actually received that link already in the reminder today, if you haven't noticed that. But with that, I'd like to thank you all. Thank you, Ilya, once again, and we'll see you in August.
Thank you very much, Maxim, and goodbye, everybody.
Bye-bye.